The next generation of health activity monitoring is greatly dependent on wireless sensing. Localization and detection of human motion and activity have been of great interest in to many researchers in recent years. This reasons to the technological advancements in the fields of wireless communication, computing, and sensing, through which studies have emerged that made significant contributions to the field. A system that is capable of identifying the activity and the position of the subject has numerous applications. This includes applications in healthcare, applications in energy management, and applications in security. Similar systems that are present in the literature performed a distinct functionality, a distinct task, either activity detection or localization. For instance, the activity detection systems presented in some of the studies reported in the paper have reported high accuracies of 91% and 94% to detect multiple activities whilst using devices such as the USRP N210 model. Other systems that looked at localization utilized technologies such as RFID for localization and tracking, software-defined radios such as USRPs, commercial off-the-shelf Wi-Fi devices, frequency-modulated continuous wave radar, and impulse radio ultra-wideband. In our paper, we take this a step forward to improve on the studies in the literature by combining the activity detection feature and the localization feature into one system that performs these two functionalities with high accuracies. And I can summarize the contributions accordingly into the localization of activities in 3 different zones within a room, identifying the direction of movement in 3 different positions within a room, and identifying whether a room is occupied or empty. This brings us to the technical side of the work. So I've divided this into the hardware specifications and the software specifications. On the hardware side, we've used the USRPs, which are software-defined radios, and in particular the X3 X0 series, so the X300 and the X310. We've used them to collect the data and set them up as seen here in the figure, where we've used 2 PCs running Ubuntu virtual machine on them, and these virtual machines where the scripts, the Python scripts for machine learning, Python scripts for collecting data were running on them. The specifications that we've set the system to in terms of operating frequency, as seen here, was 3.75 gigahertz. The number of OFDM subcarriers were 52, and we've set the gains of the transmitter and receiver to 70 and 50 dBm respectively. On the software side, and as discussed, as mentioned earlier, the Python scripts were running on the Ubuntu virtual machines, and there were 2 types of scripts. There was the GNU radio, which was applied to set up the USRPs and be able to configure them, and there were the ones used, the Python scripts used for extracting the data, for building the data sets, and of course for running the machine learning. And this flow diagram just shows how does the data flow from the start till a CSV file is generated and ready to be processed. So the USRP configuration script provides a text file with channel state information in them, and then the data processing script, which also runs on the same machine, extracts the channel state information from this text file and puts them into a CSV file that could be then labeled and used to train the machine learning algorithm. And this brings us to the experimental setup which we used to collect the data and test the system. as seen here in this diagram, this is a representation of the activity area that we used. The experiments were conducted at the University of Glasgow in the James Watt South building, where there is currently an active ethical application, an approved one. What we've done is we've taken a room that is quite big, but we've taken an area of 3.8 meters by 5.2, and as can be seen here, we've placed the transmitter and the receiver diagonally from each other, facing each other, and we've dissected this room, divided it into 3 zones. Zone 1 starting from the right, Zone 1, and then Zone 2, and then Zone 3, each spaced at a 1 meter distance. And within each zone, the activities took place. And the activities that were selected for this experiment were sitting on a chair, so the action of sitting on a chair, standing from a chair, so the action of standing from a chair, walking from the transmitter side, that is the bottom side of this figure, to the receiver side, and that is the grey arrow, and walking from the receiver side, which is the top side, to the transmitter side, that is represented by the black arrow. The idea was to see various basic activities and how would the system differentiate with them happening in different positions, but also if there's a distinct difference between the direction of movements, one in that case from the transmitter to the receiver, or from the receiver to the transmitter. This here is just an example to show you the difference that between the various activities performed. So these are 4 channel state information captures that were taken from Zone 1. A represents an empty room, so this doesn't really fall within a specific zone, because the way we've captured the empty data is that we've left the room and left the system on collecting data. So there isn't an empty zone, it's mainly an empty room. B represents the sitting activity, so bear in mind that it's the action of sitting and not the position of sitting, because channel state information, these changes respond to movement and not position, or not posture, sorry. C, figure C represents the action of standing, and finally figure D represents the walking from the transmitter side, which was the bottom side in the previous experimental setup diagram, to the receiver side, which was the top side of the experimental setup diagram. And you can see visually that there is a distinct difference between each of these captures, and this makes, I mean, to us, when we started collecting the data, this was gave us the notion that there is potential here to accurately differentiate between these activities within one zone. So this table here, taken from the paper, really just shows the different classes and the description of each that were considered in this experiment. So we've got a total of 16 classes with a total of 360 samples, divided as seen here. So we've got the first one, which represented an empty room, and as I mentioned earlier, an empty room means there was no human subject in the activity area. Sitting in zone 1 means performing the action of sitting at the designated location within zone 1, and if you can refer to the paper where the experimental design setup is, you can see the position of the chair. Similarly, for standing in zone 1, which was the action of standing from the chair within zone 1, walking TX RX means walking from the transmitter side to the receiver side, and vice versa for the walking RX TX. And apologies, I forgot to mention that earlier, but we've also looked at leaning forward. So leaning forward, just bending with the upper body to try and simulate the falling activity. And we've done similarly in the rest of the zones, the same activities, and 20 samples were collected for each, and it was only 60 samples that was collected for the empty room. Now, after collecting all the data as described earlier, we tested the system by performing 2 experiments. The first was testing the classification accuracy for each zone separately, meaning after collecting all of the activity data for zone 1, collecting the activity data for zone 2, collecting the activity data for zone 3, we've developed 3 separate data sets, each distinct, each having only the activities performed in that area, meaning they had a total of 6 classes: empty, sitting, standing, walking in one direction, walking in the other direction, and leaning forward. And that was the first test that we did. We wanted to see, first of all, the accuracy of detection within each zone. And with that, we can see if we could establish a relationship between where the activity is happening and the accuracy of the result. The second experiment was testing the classification accuracy for all zones combined. And that was the main aim of the paper, to see that if we feed a system with multiple activity classes occurring or happening in different positions within a room, is it going to be able to differentiate between them or not, and actually localize where the activity is happening. So from the first experiment, the first set of results are shown here. This here is the confusion matrices for each machine learning run on each of the data sets created for each zone. So the top confusion matrix was from the data taken from this zone, zone 1. As you can see, the first class was empty room, leaning forward, sitting, standing, walking, transmitter to receiver, and walking receiver to transmitter, and that was all the data collected from the first zone as seen here in this diagram. And as you can see, the classification accuracy, and we've used the tenfold cross-validation, gave 100%. The system was able to differentiate between these particular classes, and to further interpret this, that the system was capable of not only differentiating between different activities, but similar activities such as the walking from the transmitter to the receiver and from the receiver to the transmitter, but it was actually capable of detecting that the direction here is different. And that was a very interesting insight and interesting result that we got in this from this paper. For the second zone, we did a similar test. We've collected the data, created the data set, processed it, and ran the tenfold cross-validation. We got a very high accuracy as well, 97.5%, but compared to the first zone, that was 2.5% less accurate. And as you can see, that the leaning forward class was mistaken for sitting, similarly with the standing, which was mistaken for walking from TX to RX, and finally walking from TX to RX, which was mistaken for leaning forward. So it is a confusion matrix after all, so you can see the confusion here in some of the samples. And when we look at the second test, I'm going to shed some light on what possible reasons could be for this confusion. Similarly with zone 3, we ran the test and it gave about 95% accuracy with even more confusion. And the first really conclusion point, and that may be a bit early in the presentation, but is you can see that there's a degradation in the accuracy as you move away from the transmitter. However, further, of course, investigation is definitely needed to know this for sure, but that was one of the points that we wanted to look into from these experiments. Now, after running the first experiment, we did combine all data samples together into one data set represented by 16 classes: empty, sit, Z1, stand, Z1, meaning sitting in zone 1, standing in zone 1, etc. And these classes are the same as the ones shown in the previous slides of the table. The accuracy recorded here was 93.6%, slightly lower than the accuracies shown from the first experiment, but it does show very promising results because it was capable of differentiating between sitting in this zone and sitting in the second zone and sitting in the third zone with higher accuracy. And that actually showed the promise of such a system to be able to develop using only channel state information mined from a USRP device, or similarly from over-the-counter Wi-Fi devices or any source of wireless signals. They can actually develop, using machine learning and using an intelligent approach, you can actually develop a system that is capable of telling you what the activity is, but also localizing it and telling you where it happened. And to wrap up and conclude this presentation, in this paper we presented a novel system that utilizes the USRP devices working as software-defined radios to detect multiple activities performed in different locations of the same room. And with the presented results, such a system can be used to develop systems for performing fault prediction and detection by inferring it based on the leaning activity. It can also utilize the direction detection to know where the elderly or the person who fell, which direction they fall, and you can then infer if they hit the head in a cupboard or something. Secondly, monitoring elderly people who live alone without invading their privacy to ensure they are active and conscious. And the utilization of the occupancy feature, that is knowing if a room is occupied or not, in energy saving systems, emergency evacuation and security systems, by also monitoring the direction of movement of any unauthorized subjects.